let's talk. I'd love to know more. Okay, so guys, here's what we're going to do today. It all actually ties back to Rachel's question a minute ago when we were talking about water heaters, and she asked the question, why does it corrode the zinc before the steel, the iron? And we talked about this idea of just limited opportunity, because once it corrodes one, it can't corrode the other. But guys, fundamentally, there's an even deeper underlying question, which is why zinc? Why magnesium? And the answer to that question comes down to a question of comparison. And this is what we're going to do today. So guys, what we're going to talk about today, really, and maybe an even more fitting way of explaining this is, don't write this down, but let's go back to something that's maybe even more familiar to you. So guys, we've got zinc, we've got copper ion, we've got zinc ion. It's our friendly neighborhood battery, right, that we've torn apart last time, and we just got done re-tearing apart today. Guys, which way does the current flow? Left to right or right to left? Left to right, right? So we know the current's going to flow in that direction. The question is why? And the answer is fundamentally, it has to do with the nature of zinc, and it has to do with the nature of copper. And so how you choose to think about this is up to you. But guys, fundamentally, the idea is you could think of it this way. You could say that copper ion is more easily reduced than zinc ion. Does that make sense? Copper ion is more easily reduced than zinc ion. And so, or you could say that zinc atom is more easily reduced than copper atom. Thank you, oxidized, my bad, thank you. Is more easily oxidized than copper atom. And guys, however you choose to think about that, so let's rehash. We know that this is going to go in this direction and this goes in this direction. So why does that happen? And again, we could think of it as being copper ion is more easily reduced than zinc ion, or we could think of it that zinc atom is more easily oxidized than copper atom, and those two are always hand in hand. But guys, however you choose to think about it, just a second, however you choose to think about that, guys, we're familiar with the idea relative to zinc and copper. But what if they are not familiar pairings, and you need to be able to think through what can oxidize what, or what can reduce what? And guys, when we talk about that, we're talking about what are called redox agents, and that's what we're going to talk about in just a second. So Talmadge, go ahead. That's a wonderful question. Yes, good. And yeah, right. So, right. Atoms can't do math, right? Atoms don't know that they have a voltage assigned to them that's on a chart that we don't even get to use on the test anymore. So guys, how is it? It's not like these atoms get together and zinc and copper get together and they negotiate. Hey, you got a reduction potential of 1 point and I got 2, and so how about if you give away electrons? It doesn't work that way. So fundamentally, what is it about the atoms? And it's not as simple as this, but a lot of it's electronegativity. But another portion of it that's going to be important for our conversation today is how much empty space they have in their valence shells. So for example, did that make sense, you guys? So do you understand Talmadge's question? Because it's important. He's saying why? Why is it that zinc is better at being oxidized? Why is it that copper ion is better at being reduced? And it does have something to do with electronegativity, but it also has something to do with capacity. So guys, for example, this. Imagine that we are looking at a fluorine atom. What is fluorine going to want to do with electrons? Take them in or give them away? Fluorine is going to want to take in electrons. So guys, what about this? Pretend that's not there. I want to leave it there for reference, but pretend it's not there. Fluorine ion. What is it going to do with electrons?
Nothing.
See where we're, but that would be nothing, right? So guys, what is fluorine ion going to do with electrons? Let's look at our options. Can fluorine ion take in electrons? Why not? It's full. So it cannot be an electron taker-inner. So what's the only thing left that it can do? Give them away. So guys, fluorine ion can only be an electron giver-awayer. But is it going to be a very good electron giver-awayer? No. But understand that's all it can do. It can't be an electron taker-inner. It can only be an electron giver-awayer. No, because it's got to do, we're assuming it's going to do something. And so guys, the idea then is this. Fluorine atom is really, really good at taking in electrons. So guys, we're going to now make the transition to the big idea. Fluorine atom is really good at taking in electrons. Guys, what do we call taking in electrons? No. What do we call taking in electrons? Reduction, right? So guys, think about this. We talked about this 2 days ago. So match this idea. So fluorine is really good at taking in electrons. And when fluorine takes in electrons, what happens to fluorine? It is reduced. But what is it doing to the other element? So guys, if I'm another element over here and I run into fluorine, and fluorine takes my electron, because we've identified fluorine's good at taking electrons, right? But they got to come from somewhere. So if I'm another atom and fluorine just stole my electron, what just happened to me? I was oxidized. Guys, that, and you don't need to write any of this down. I'll give this all to you in summary in a minute. Guys, that makes fluorine a strong oxidizing agent. Think about that. Fluorine, and you guys know this, right? This is why it's such a great example. Fluorine is the most electronegative element on the periodic table. So guys, fluorine, because it's so good at taking in electrons, when fluorine takes in electrons, it's being reduced. But those electrons have got to come from somewhere, and whoever it is, when fluorine steals those electrons, this guy is being oxidized. So when we talk about agency, we're talking about what these atoms do to the other guy. And so fluorine, because it's really good at being reduced, is called a strong oxidizing agent because it's really good at causing oxidation in someone else. Does that make sense? Okay, now let's go to fluorine ion. Again, let's remind ourselves, can fluorine ion take in electrons? At all? Not at all. Guys, fluorine ion is physically incapable of taking in electrons. Why? It's full. So guys, if fluorine ion cannot take in electrons, what's the only thing it can do? Give them away. But guys, is fluorine going to give away electrons very well? No, but it can. So guys, imagine if fluorine ion gives away an electron. So if you give away an electron, what's happening to the fluorine ion? Oxidized or reduced? It's being oxidized, so what's it doing to the other guy? Reducing it. But guys, this is what is called a weak reducing agent because it's not very good at it. Does that make sense? Go ahead. Yes.
So there's an inverse relationship with that?
Yes. So hold on. Before we get too far afield, guys, let's relate this to the table that you have in front of you. Do you see fluorine and fluoride ion? Very top, right? Guys, literally do this. I really want you to do this. Take this table and split it in half right down the yields arrow. Then, guys, split it in half horizontally right through hydrogen, which is our 0 point. Right through the hydrogen. Right through the hydrogen. Okay. So now, guys, notice what we've got. Up here in this upper left-hand quadrant, because we'll talk more about this in a second. Up here in this upper left-hand quadrant, we've got fluorine, right? And you'll notice that it is F2. We just looked at an individual fluorine atom, but it actually exists as F2. Its diatomic logic is the same. So guys, what did we decide about F2? What is it really good at doing? Taking in electrons, right? That means it is being reduced, which means what does it do to the other guy? Oxidation. So all of these elements in the upper left-hand quadrant are strong oxidizing agents. Notice they get weaker as you go down, but they are all called strong oxidizing agents. They're all strong. Now, guys, if that doesn't make sense that they're all strong, drink in this thought. Let's use fluorine, F2, as our example. So are we all okay with the idea that fluorine is a strong oxidizing agent? Is that okay? Does that also mean that fluorine is a weak reducing agent? It does not. Guys, fluorine cannot be a reducing agent. You cannot pry electrons away from fluorine. Okay? So don't get this misconception that if it's strong of one, it's weak of the other. Fluorine is a strong oxidizing agent, which does not also make it a weak reducing agent. It can't be a reducing agent. But where is the reducing agent? On the other side. Guys, fluoride ion is our weak reducing agent. And what is it that allows fluoride ion to function as the weak reducing agent? The extra electron that it picked up. It's full. So guys, in the upper right-hand quadrant, we've got our weak reducing agents. So what makes them reducing agents? They've got extra electrons. What makes them weak? They're strong, so they don't want to give them up. Does that make sense? Not well. So the idea is this. If we look at the right-hand side and if we look at fluorine, fluoride should only have 7 electrons. I'm sorry, fluorine should only have 7 electrons. Fluoride has picked up an extra electron. Now it has 8. That's the negative charge. So now fluoride ion has an extra electron that it shouldn't have. We've got 7 protons, 9 protons, 8, 10 electrons because of the 2 in the S. Doesn't matter. But we've got an extra electron. And because that extra electron is more than the number of protons, it is possible to pull that off. Not very well, but it can happen. So that makes this a reducing agent. It can give away electrons. It just doesn't do it well because it's so strong, it holds on to them pretty tightly. Is that okay? Okay. So now, guys, let's do this. And this is brilliant. For those of you, I know that Anna loves this YouTube channel, Veritasium. And then if you've ever seen Veritasium or Physics Girl, those two are friends. I think they should get married. Anyway, I'm surprised they haven't. But have you seen the video that they did where they were trying to figure out how to determine the value of pi 3.14 using darts? It was lovely. Anyway, it doesn't matter. So, and there was a little love tension. But guys, they actually, they've done this wonderful video that talks about reasoning through extremes. It's actually relative to a question of whether or not a boat will float. And it's a fascinating question because you're going, wait, I think it'll float. No, it won't float. Yeah, it'll float. Wait, no, it won't float. And it's really interesting because the scenario, I can show you the video later, the scenario is really splitting hairs and you're like, oh, wait, and you can reason your way into either answer. But then it's interesting because the girl from Physics Girl sort of steps into the middle of the conversation and she's like, if you want to think through this, what you need to do is think about extremes. Don't use the example that we've given you, which puts you in this position where you're not quite sure. Look at the extremes. Because if the logic makes sense in extreme examples, it also holds true in examples that aren't so extreme that you can't clearly see the answer. It's called Reasoning Through Extremes, and it's a really fascinating video. We may have time that I can show it to you. Anyway, so guys, that's what we're doing right now. We're reasoning through extremes. So we looked at the one extreme, which is fluorine and fluoride. I even did that right relative to you. Now, guys, let's go to the bottom of the table and let's look at our other extreme, which is going to be lithium, right? So if we go down to lithium, let's look on the left side, and I'll just do it like this. On the left side, we've got lithium ion, and then on the right side, we've got lithium atom, okay? So guys, here's what we've determined. We have determined that the left-hand side is our oxidizing agents. And what does it mean to be an oxidizing agent? Give away electrons, right? No. Oxidizing agents are giving them away or they're taking them in? They're taking them in. So guys, let's talk about lithium atom. Lithium ion. Sorry. Lithium ion. Can lithium ion take in electrons? How do you know? It's got a positive charge, right? It's got space. What do you have to do to lithium atom to make it lithium ion? Take away an electron. So guys, lithium's got space. It can take in electrons. But is lithium going to be very good at taking in electrons? It's not very electronegative. So guys, this is an oxidizing agent. It has the potential to take in electrons. It's got room. It can take them in. The problem is that lithium is such a weak element and ion that it doesn't do it very well. So it can take in electrons. It just doesn't do it very well. Now guys, does that sit okay with you? So now try the other side of this coin. If lithium ion is a weak oxidizing agent, does that mean that it's a strong reducing agent? Why not? It doesn't have any valence electrons, right? Guys, lithium ion doesn't have any valence electrons. It gave it away. That's how it ended up positive. Guys, lithium ion doesn't even have any valence electrons to give away, so it can't be a reducing agent because it ain't got anything to give. So now let's go over here to lithium atom. Can lithium atom be an oxidizing agent? Think about that. Can lithium atom be an oxidizing agent? What does it mean to be an oxidizing agent? Take in electrons. Can lithium atom take in electrons? Why not? Two reasons. One, it's full. Two, it's weak, right? Guys, lithium ion is like the least likely guy on the planet to take in electrons. One, it's so weak it can't steal from anybody. And two, even if it could, it doesn't have room for any electrons. So guys, this is not an oxidizing agent. But what about a reducing agent? Good night. What makes lithium ion a good reducing agent? Same things. It's weak and it's full, right? So guys, that makes this a strong reducing agent. It's strong and it's a reducing agent, just a second. It's a reducing agent because it's got lots of electrons to give away, and it's strong because it's weak. Yeah. It's got two, its sublevels are, right, so 1s, 2s, that's the electron configuration for lithium. The 1s is full, the 2s is full. Oh, wait, oh, I'm sorry, no, my bad. But it's as full as it can be. Okay, so, sorry, you're right, it's not full. So let's go back to the idea. So here, let's just go all the way back. So guys, what's that? What did I just draw? That's lithium ion, right? It gave away its one electron. This is lithium ion. So the idea is lithium ion, it can only be an oxidizing agent. Why can't it be a reducing agent? In order to be a reducing agent, what does it need to do? Give away electrons. And guys, why can't we get those electrons away from lithium? Because they're so tightly bound. 3 protons, 2 electrons. Remember when we did PES? Remember that idea? The idea is those electrons are going to be very tightly bound because they are unshielded inner core electrons that are held right up against 3 protons. They're going to be hard to get off. So now we understand why lithium ion can't reduce. But why can it oxidize? Well, guys, it's got space. There's room there where we can put electrons. The problem is that the nucleus is not that strong, so it doesn't do it well. So that's why lithium ion is a weak oxidizing agent. But guys, what about the idea that lithium atom is a strong reducing agent? Well, now we put in that electron. This is now lithium atom. So guys, what do we know about the electron? Ooh, there's the word. What do we know about the electron binding energy for that electron? It's pretty low, right? It's shielded now from a relatively weak nucleus. So this electron is not very tightly bound. It goes away really easily. And when lithium atom loses that electron, it causes reduction very easily in something else. So that makes it a strong reducing agent. Does that make sense? Yeah, thank you for calling me back on that idea that it's full. I guess what I meant was it's as full as it can be. But that was the idea. Okay, you guys good? Yeah. Well, they're not, wait, cesium? So, well, they're close, right? I mean, they're only off by, a tenth, 3%. But your question is still good. Why would lithium be a better electron giver awayer than cesium? I don't know. I'm not sure. But it's interesting because your question takes us back to what Talmage asked that sort of started this conversation, which is what is it about these atoms that determine where they sit on the table? And guys, so let's answer that question. The things that we need to worry, the logic that makes sense to us is their position on this table is a function of whether or not they're full and whether or not they're strong. Do you know what I'm saying? But then understand, Ammon, your question is bringing out the idea that that's not the complete answer. Their general location on this table, which is all we need to know, is whether or not they're full and whether or not they're strong. The finer points that explain why cesium has a higher reduction potential than lithium, I don't know. I'm frankly not sure. I've never needed to tease that out because 1, I understand the general principles, and 2, I've always had this table at my disposal. But understand, even when they gave us this table on the AP test, they would never ask you, why is it that lithium and cesium are where they are on the table? They would ask you, why is it that lithium's here and fluorine's here? But they wouldn't ask you to tease out those little differences. Is that okay? Let's don't. I'd love to know, but not now. Yeah. Yeah, no, and it's not at all. But guys, let's make this transition then. Do you see what I gave you? Yeah, it's what you wrote on your reduction potential chart. Ooh, can I tell you a nasty story? In 2002, 3, maybe 4. They switched it on us. Prior to 2003, I think it was, they actually used to give us a oxidation potential chart. And then all of a sudden, without telling anybody, in 2003, on the test, they switched it to a reduction potential chart, flipped the chart upside down on us and didn't tell anybody. That was awesome. Everybody got those questions wrong because you're not looking at the numbers, right? You're looking at relative possessions on the table, and sure enough, you go back and look at the test and it clearly says reduction potential chart. But up until then, we'd been teaching this stuff with oxidation potential charts. That was awesome. So, guys, do you understand the idea of this table? Is that okay? Okay. So, guys, with that said, let's just yippee skip down here really quick. So this is the last thing that we need to talk about. So, and guys, okay, so we've already talked about it. Let me just lay this before you. So up until now, we've been looking at oxidation reduction reactions through the lens of batteries. And when we think about batteries, as we just did in the previous homework, guys, when we think about batteries, we always write them so that they have positive voltages. Do you remember that I suggested that when we were looking at that last page in the homework? I said, hey, you'll notice that all of these have positive voltages. And the reason that we write them so that they have positive voltages is so that we've got the cathode minus the anode, and that then gives us a battery that's written properly. Well, guys, it turns out that these concepts relative to these voltages don't just have to apply to batteries. There's lots of other oxidation reduction processes that aren't batteries. And if we want to study the spontaneity of those cells, of those reactions, all we've got to do is this. Rather than talk about these things as being cathode and anode, all we've got to do is talk about the reduction and the oxidation. And I think I have this in my notes. If I don't, we'll throw it in. Yeah, so guys, the idea is this. All we've got to do is that, and it makes the equation generic. So when we apply this to a battery, we say cathode minus anode, because those are the two parts of a battery. But when we talk about all sorts of other oxidation reduction processes, we understand that the cathode is reduction and the anode is oxidation, and now it applies to anything. So now we can take any redox process and we can figure out whether or not it's spontaneous as written. All we've got to do is know the reduction potential for the cathode, the reduction potential for the anode, the reduction and the oxidation, subtract the two. And guys, if we end up with a positive voltage, what does that tell us? It's spontaneous. And if we've got a negative voltage, what does that tell us? It's spontaneous in the other direction. Does that make sense? Okay. So guys, that's it. We're done. Okay, now I've got to make a decision. Is this on the AP test? On the equation? It is there. We should talk. Yeah. This is, I'm glad they didn't take this away. I thought they had, they didn't. Let's talk. This is interesting. So guys, cast yourself back now to chapters 5 and 19. Do you remember we started in chapter 5, we talked about thermochemistry, we talked about enthalpy, then we jumped to chapter 19, we talked about entropy. We could even review for the test for a minute. Guys, and we related that to spontaneity. So thinking about enthalpy, which is heat, what kinds of reactions tend to be spontaneous? Exothermic. And then when we brought in the idea of entropy, which is disorder, we then said relative to entropy, what kind of reactions tend to be spontaneous? Disorder goes up, right? Increasing disorder. And guys, remember then we talked about the idea that when we bring those two potentially competing ideas together, enthalpy and entropy, in order to finally figure out whether or not a reaction is spontaneous, what is the only sure thing we can go to? Gibbs free energy. And guys, if you don't remember, you may want to scratch it down. The idea that delta G is equal to delta H minus T delta S. And that's in the AP equation sheet. So guys, what delta G values guarantee spontaneity? Negative, losing energy, right? So negative delta G's would suggest spontaneity. Well, guys, guess what? Now we've got another predictor of spontaneity, and that would be the E cell. E cell is equal to the reduction potential at the how do we write that? No, we're getting there. Just E reduction. Yeah, let me do this again. So the reduction potential at the reduction minus the reduction potential at the oxidation. So guys, here's what we know. What delta G values tell us spontaneous? Negative. What voltages tell us spontaneous? Positive. Well, guess what? It turns out that both of these are predictors of spontaneity. So Gibbs free energy predicts spontaneity, negative delta G's, and voltages predict spontaneity, positive voltages. So now we have two predictors of spontaneity. Of course, if it's not a redox reaction, then the E cell doesn't count. But if we are looking at the spontaneity of an oxidation-reduction reaction, these two are related. And guys, do you see the equation there on your AP equation sheet? It goes like this. The equation is delta G is equal to negative NFE. But guys, this E is E cell. So here's one variable, here's the other variable, and we find out that there is, and we would expect this, right? We find out there's a relationship between delta G and the voltage of the cell, but because they both predict spontaneity, that seems reasonable, right? But you'll notice the difference. Negative delta G's and positive voltages both tell us spontaneous. That's why this negative sign is here. It respects the fact that positive voltages and negative delta G's both talk about spontaneity. So now the only thing we got to know is this. What is N and what is F? Does it tell you in the equation sheet? Yeah, so F is Faraday's constant, which is given to you on the equation sheet, and N is the number of moles. But guys, the number of moles of what? The answer is electrons. It's the number of moles of electrons. So for example, if we have this reaction, what's N? 2. Copper gains 2 electrons, zinc loses 2 electrons, so it's the number of electrons being exchanged. So if you were trying to figure out N for this process, copper gains 2, zinc loses 2, so N would be 2. Because those relationships are molar as well as particle by particle. So using then this equation, you can move back and forth between delta G's and voltages. Yeah.
The electrons, so if we were to, hypothetical, they gave us a redox reaction, they said balance this redox reaction. That the number of electrons in the very end.
Yeah.
We cancel.
Right.
Those are the numbers.
Exactly, which is in this case 2. Yep. You guys good? All right. Let me throw some homework your way. Guys, can you believe we have one more day of lecture in this class?